All right, so today we're going to look at polynomial graphs, and I actually want to start further down in the notes right here. I'm going to pick up where we left off yesterday. So yesterday we talked about what a polynomial is, and we just said that polynomials need to have exponents that are positive whole numbers, and that's still true, but there's a couple other characteristics that they should have as well, specifically about their graphs. Their graph should be nice and fluid, should have ends that go on forever, either to positive or negative infinity, like we saw yesterday. But what they should not have are sharp corners, holes, or asymptotes. So if we see these three graphs, we can see that graph A is a polynomial. It's nice and smooth. It goes on forever to the left and to the right. No holes or asymptotes or anything like that. However, in graph B, we have a hole here, which makes this not a polynomial. And in graph C, this has a sharp corner, which says that this cannot be a polynomial. So beware that when you're graphing your polynomial graphs, make sure they're nice and fluid like this one. Okay, so yesterday we talked about end behavior, right? Whether the function was positive even, negative even, positive odd, and so on. And we know that tells us what the ends of our polynomial graph are. Today we're going to look a little bit deeper into these peaks and valleys in the middle. We know the polynomial graph is going to go through the zeros up and down, and then our end behavior will pick up. So the zeros, the number of zeros we're going to have will be at most the same as the highest degree of the polynomial. We talked about this yesterday. So for example, x to the fourth will have less than or equal to 4 zeros. So if you have a polynomial with the highest degree of 4, you're going to have 4 zeros or fewer. One thing we haven't talked about that will come up today are turning points. If you have a graph, or if you're graphing a polynomial, whatever the degree of the polynomial is, it will have one less than the number of turning points. So a polynomial of x to the fourth will have 3 or less turning points. So it will all make sense when we look at these examples. So here's a polynomial graph. We see it goes on forever and ever, left and right, and it's nice and fluid in the middle with those peaks and valleys. So we can start analyzing it by first looking at the zeros. It has x-intercepts at -4, -2, 1, 2, and 4. So we can list out the zeros and say the zeros are at -4, -2, 1, 2, and 4. We can then look at the end behavior and say the right arrow is pointing down, which means the leading coefficient is going to be negative, and the left arrow is opposite that, which means it's going to be an odd degree. Now, putting together the zeros with odd, we can count 1, 2, 3, 4, 5 zeros, which matches an odd degree. So I would feel pretty confident that this polynomial should have a minimum degree of 5, because remember, the number of zeros should be less than or equal to the degree. So if it's equal, it would be 5, or it could be 7. Since there's 5 here, the degree could be a little bit higher, but this makes the most sense. We can confirm also by counting the number of turning points. So the turning points are where our graph changes direction. Like notice it's decreasing to increasing to decreasing. So there's a turning point here, 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 and here. So 1, 2, 3, 4. That's one less, so we have 4 turning points. That's one less than our degree. So everything matches up. We can give this graph these characteristics. In the same way, if we're to practice it one more time, we can look at this polynomial graph and say, well, there are zeros at -3, 1, and 4. However, hopefully you're noticing at 1 that it's bouncing off the x-axis. Because of this bounce, we know this 0 is going to have a multiplicity of 2. So we can say the zeros are at x equals -3, +1 with a multiplicity of 2, and then +4. So counting, we can see 1, 2, 3, 4 zeros. Does that match with the end behavior? Let's take a look. So the right arrow is pointing down, which means it has a negative leading coefficient. The right arrow is also pointing down, so the same direction, which means it's even. 1, 2, 3, 4, that matches an even number, so we can say the minimum degree would be 4. We can confirm that by counting the number of turning points. 1, 2, 3 turning points. That is 1 less than the degree. So using all this knowledge and characteristics of our polynomials, we can analyze our graphs, and then we can put it all together and then actually graph our own polynomials, which is what we're going to do with these examples. So just like before, we need to find our zeros first. Luckily, this polynomial that was given to us is already in factored form, so we can set all of the factors equal to 0 and say our zeros are at -7, -3, multiplicity of 2, notice that exponent up top, and then at 5. So we can put x-intercepts at -7, -3, and I'm just going to put a little times 2 there to remind myself that it should bounce off, and then at 5. Then we can go back up and look at the polynomial and ask ourselves, is this function positive or negative? Is the leading coefficient positive or negative? Well, we can look 1/3 is positive, x is positive, a positive squared is positive. So all of these positive times positive times positive, all of these positives being multiplied together is positive. So that means our right arrow is going to go up. And then if we count the degrees, this is x to the first, x squared, x to the first. So 1 plus 2 plus 1 is 4. So this is an even polynomial, which means both of them will face up. So we can put those arrows now onto our graph. The right arrow, so from the from the 0 all the way to the right, it's going to point up, and the 0 all the way to the left is going to point up. So we've done this already. We've kind of like talked about this, and now comes the fun part. Now we get to graph the rest of the peaks and valleys inside. So we know that it could be a 4th degree, so we're going to turn once, twice, 3 times maybe, and we need to bounce off of this 0. So what we can do is extend this arrow down. We can turn, bounce, and then turn again and form our peaks and valleys for the polynomial. Now, how far you go down on these or how exaggerated you make the peaks and valleys is totally up to you. I would take very gradual ones, or how I graphed it, or you can go down low or whatever. It doesn't really matter to me. What I'm looking at is that you're going through the zeros nice and smoothly, bouncing where you need to, and then finishing off with the correct end behavior, okay? So that's how the general form, like what I expect when you graph a polynomial. Now, this polynomial was given to us and it was already factored. So if it's not factored, we would have to do that preliminary work. So if we look at number 2, we could factor this taking out a GCF. And then we can factor the inside polynomial. So 2 numbers that multiply to -20, add to -1 would be -5 and +4. Once it's factored, then we can use the 0 product property, set each of the factors with x equal to 0. We can get our zeros are 0, 5, and -4. There are no powers to any of these factors, so no multiplicities, and we can just put zeros at -4, 0, and 5. So we know where our polynomial is going to cross the x-axis. Then we can go back up and say our leading coefficient is positive and our exponent is odd. So that means our right arrow is going to go up. Our left arrow is going to go in the opposite direction. So on our graph, our right arrow is going to go up. Our left arrow is going to go in the opposite direction. And then we get to connect the dots, making sure that it goes through all the zeros. So we can just kind of finish the curve off like this. Again, how exaggerated you make it, if you want to go like way up high and way down low, that's totally up to you. I'm fine with just something like this to show that there's some curves. There's 2 turning points with a power of 3, and the end behavior is all correct. So that's just the main idea from today, is I just want to make sure we can put together the zeros with the end behavior and connect the dots to make a general graph of our polynomial. If you have to go back and rewind any of those things, go ahead and do that. There's one last topic that we need to go through, and that is this intermediate value theorem. And if you'd like, you can take a picture of this. It's a lot of work writing down. So just listen, and you can take a screenshot and insert this into your notes. I just want you to understand what the intermediate value theorem says. So when we have a graph of a polynomial, it's really easy to literally point out where the zeros occur, right? We have a 0 at 2, at 1, and somewhere in between 3 and 4. And if we were to ask, hey, is there a 0 between x values 3 and 4? We could just look at the graph and say, okay, here's 3, here's 4. Does the graph cross the x-axis in between that interval? And we could clearly see, yeah, it sure does. But how do we do that? How do we answer that question? Does a 0 exist on this interval without the graph? And the intermediate value theorem says that if you have an interval, let's say if we're looking between a and b, two x values, a and b, as long as their corresponding y values have opposite signs, then we can say that a 0 exists between a and b. So the only thing we need to do then is if we're given a polynomial and we're asked if there's a 0 on a certain interval, all we have to do is take those two x values and plug them into the polynomial. So we do f of 3 is equal to 3 to the 4th plus 3 cubed minus 14, 3x squared, and so on. You can plug that straight into your calculator to get that the corresponding y value is negative 30. So that means when x is 3, y is, missed that negative 30. And we can do the same thing by plugging in 4. We get that when x is 4, y is 72. So we just do a little evaluating, which we've done before, but then we apply the intermediate value theorem, which says if the x values or if the y values have opposite signs, then they must cross the x-axis and a 0 must exist on that interval. And we can clearly see that when x is 3, its y value is way down here. When x is 4, its y value is way up here. Of course, to connect from here to here, of course we're going to have to cross through the x-axis. So it makes sense that if the y values have opposite signs, at some point we're going to have to cross 0 to go from negative 0 to positive, right? So that's all the intermediate value theorem says. There's two examples here. Again, you can take a screenshot. I'm just giving you different polynomials, different intervals. You just need to know that you're going to plug in the x value into the x to get the corresponding y for both of these x values. Again, these are both x values, so we're going to do f of 0 and f of 1, plugging them in. When x is 0, y is 2. When x is 1, y is negative 12, and we see that they have opposite signs. If we were to sketch this out, let's see, when x is 0, y is positive 2. When x is 1, y is negative 12. So do you guys see when we connect these two, we're going to have to cross the x-axis here, right? At some point, to go from a positive y to a negative y, we're going to have to cross through 0. So yeah, because the y values have opposite signs, a 0 exists. And the same thing, coincidentally, happens with number 2. When we plug in negative 1 and positive 1, the y values have opposite signs. So because the y values have opposite signs, a 0 exists on this interval. Okay, guys? I hope this all makes sense. Rewind, copy, take down, make sure you're taking thorough notes, and then I'll be back to answer any questions tomorrow. We'll see you later.